In this video, we'll continue discussing the types of ligands, and in particular, one particular type would be polydentates. Polydentates are something like this: EDTA, ethylene diamine tetraacetate, short for EDTA. They have lots of lone pairs that are connected, well, not yet, but they have lots of lone pairs that have the ability to attach to the transition metal in the middle if they were to form as a ligand. So it's not just one area, but multiple areas. This is possible because the EDTA structure is quite large and has multiple available electron donors in order to attach to the metal. Here is a metal in the middle, so M representing metal, so I want any of the transition metal, and this would be the EDTA written in a line angle structure form. So you don't see the carbons here, but you see nitrogens and some oxygens. So the dashed line represents where it's attaching to. So if you look at it, this oxygen, I will go ahead and star it. That oxygen would be something like here, star. This oxygen over here, that's this one. Then you see this nitrogen, that will be this one right here. Then you see another nitrogen, that's this one, and that's over here. Here is an oxygen off to the side here, and there's this oxygen that's right here. So there's 6 points in which this metal's attached to by just one molecule. It's a large molecule, but one molecule is sort of surrounding that metal via bonding to the metal. So hence this is called the polydentates because it's more than just one lone pair that has the ability to bind to the metal ion. Now you might wonder, is polydentate same as a bidentate? No, bidentate could only attach to two. So you can say the bidentate is a type of a polydentate. Here's another example, and this would be a porphyrin ring. It's found in hemoglobin of your red blood cells. And you can see the multiple attachment of the nitrogen in the middle would be iron, and this is a tetradentate, so four lone pairs are being attached to the iron right here. This is in your reference sheet. It gives you a very nice organization between a monodentate, bidentate, and polydentate. There are more, of course, but I won't test beyond this particular data, this particular table. So make sure you take a look at it and find where it is in your reference sheet because I will refer to them more frequently. All right, there are some names I like to cover or some vocabulary words based on the types of ligand, in particular the polydentate. Chelate is a complex ion that contains either the bidentate or polydentate ligands. So all of these right here, these are there. You could see that there's a metal in the middle. So there's nickel. Here's my iron. Here's my cobalt. These are all transition metal in the middle. And on the right side, you don't see any transition metal. In fact, the right side, this is just a polydentate that hasn't been attached. The ones that are attached to the transition metal, that's considered to be a chelate. The one that is not attached but has the potential to attach would be considered to be a chelating agent. So the chelating agent has the ability to bind to a metal. For example, this one chelating agent is EDTA. And this guy has the ability to surround a metal. And sometimes EDTA is actually injected into patients when there's a high level of metal and it needs to sort of circle that in and trap that metal. And so EDTA is actually could be introduced to a patient. So that's chelating agent. Chelate is the guy that already has the transition metal attached to it. So it's already been, I guess you could say, chelated. All right. Now, I do want to compare the difference between something with a bidentate or polydentate versus a monodentate. One is more stable than the other. So let's look at this. Does this one have a monodentate, bidentate, or polydentate? Yeah, hopefully you were able to say mono because all the nitrogens that are attached are not connected to each other, but rather they're by itself. So these NH3 also in your reference sheet, you'll see the ammonia is a monodentate. So this right here, this ligand is a monodentate. What about this one? This one, I hope you were able to see that this is a bidentate. Okay, bidentate. That's because here's nitrogen. This is a one entire molecule that is in two areas. It's attaching to the nickel, and that goes for all of these guys. This is En. Okay, ethylene I want to tell you right off the bat that the monodentate has less stability than the one that's going to have the complex ion that is going to have a polydentate or bidentate. So why is this complex less stable? That's because when a monodentate has a potential to leave, okay, so they're just going to kind of leave and come back. They can come back. But once they do leave, they can have another ligand kind of sort of takes its place. For example, for this one, NH3, say that sort of leaves and it wants to come back, but there's another ligand that just floating around, say water that's floating around, it can take its place fairly quickly. Whereas in the bidentate, if one part of the bidentate ligand leaves, so say this one tries to leave, the thing is other part is still intact on it. So it doesn't easily fall off, so it'll just reattach itself. So this guy right here, this other one doesn't believe it stays intact. So the other one will just sort of leave. This one right here in H2 might leave for a real quick, but they're like, okay, never mind. I can't leave fully because I'm already attached to here. So it'll rebind back to nickel. So hence why the complex ion with multiple attachments, so multiple of the polydentates ligands are going to be the one that has a more stable complex ion versus a complex ion with just monodentate. All right, let's do a learning check. Following is an image of EDTA calcium. You're going to label the chelate, the chelating agent. Is this a stable structure? So pause and come back. So coming back, this EDTA itself is the chelating agent. The whole entire complex right here, because it has calcium in the middle, this is the chelate. So I guess you could sort of say any coordination compound or ion, complex ion with a bi or polydentates, these are all considered to be chelates. Is this a stable structure? And the answer is yes. Why is this very stable? It's actually stable than the ones we talked about previously in the other slide, and that's because it has 6 bonds. It has 6 coordination number per chelating agent. So per ligand, per polydentate. This polydentate has ability to attach to on all single site, and there's only one EDT here. It's not multiple EDT, it was just one. And because it's a polydentate, it has very high stability.